Swayam Prabha. Digital India. Educated India.
Our next topic is sets and relations, and we'll start today with some basics of sets. Before that, as a quick motivation, here is some place where you would come across relations later on in computer science, and that is in the context of relational databases. So the table that you see here was a predicate we defined some time back, a predicate on two variables, x and y. And as a relational database table, this could be represented as, so it's a table called likes, and you have tuples or pairs that satisfy, for which this relation holds, right? So this kind of thing we'll be defining and working with in this topic. And what you would see is that in a relational database, the queries that you make to the database are essentially set operations. So you could make a query like, select all x's, so all entries in the first column from this table likes, where the second column has the value Alice or Flamingo. So you could write this in terms of set notation. So select all x's such that the second entry is Alice, so x comma Alice in likes, or x comma Flamingo is in likes. Okay, and this set union you see here shows up as a logical operator, or, and as we shall see shortly, that's not a coincidence. Okay, so this is just to set the context of where these things, some of these things would show up later on in computer science, but we shall see other applications also, or other aspects also of sets and relations. Okay, so some basics which you should be familiar from your high school. So a set is just an unordered collection. So no ordering, is just a collection of elements. And the examples you'll be familiar with are the set of integers Z, the set of real numbers R. These are both infinite sets. Or you could have a set like just 3 elements here called 1, 2, and 5. Or you could have an empty set which has no elements. So the empty set is denoted by this symbol, which looks like an O. With a bar through it. So we'll always have an implicit or explicit universe or a universal set from which the elements of the sets we are interested in come. Just as an aside, in developing the foundations of mathematics, there is an approach that uses set theory, and there you develop everything from scratch. Everything is defined in terms of sets themselves. So we'll not be worried about that. For us, basic familiar sets like sets of integers and real numbers will be always given. Okay, just a couple of notation that you would be familiar with. So this denotes is an element of or membership. So it says at 0.5, the element 0.5 is a member of the set R. You just read it as 0.5 is in R and 0.5 is not in Z. Note that the empty set is not in Z. Z consists of integers, 0, 1, 2, 3, and -1, -2, so forth. But the empty set is not an element of Z, therefore. However, it is a subset of Z. You could also have other subsets of Z, like this 1 to 5. Z here is a subset of R. Ignore the comma there. So that's set inclusion. This denotes is a subset of. So the set Z is included in the set R. And you could also reverse the symbol to say, and you would write Z is a superset of the empty set. And you would be familiar with the set operations like union, intersection, complement, and set difference, and we will shortly see them again. Okay, so before we see these, so let me just first show you these set operations very quickly by pictures. So here I'm using, the big box here, think of that as a universal set. So there's a Venn diagram essentially, and this darkened portion symbolizes the set S. And here is another set, set T, and S complement would look like, you change all the, so the darkened portion is what is in the set. So here the darkened portion is whatever was, is outside the box. So that is S complement. And what is inside the box is darkened here. So that is the set S. S union T in this picture would simply look like superposition of the dark portions of S and T. So that's how you could visualize S union T. S intersection T is where both the figures S and T have it dark. That's where these are elements common to S and T. And S difference T are elements in S which are not in T. So this would be a visualization of S difference T. Okay, so I expect that you're familiar with all these set operations, but let me put them in a different perspective. Okay, so let's think of sets using propositional calculus we saw earlier, and in terms of predicates that we defined earlier. So here is an example from when we define predicates. So these are universe of the domain of discourse, and here is a predicate winged. Okay, now given such a predicate, you can consider the set of elements for which it holds. For instance, the corresponding to the predicate winged, you can think of a set, which I'm calling here winged set, which is simply the set of all elements for which all elements X for which winged X holds true. And here, though, that set consists of Jabberwock and Flamingo. Flies X, flies is a predicate which is essentially the same as winged. It's a different predicate, has a different name, but the set, the flies set and the winged set are the same set, they're equal. The set defined by the predicate pink consists only of Flamingo, so it's a different set. Okay, so you could take a predicate and you could think of it as a set, as a set of elements from the universe, from the domain, for which the predicate holds. Okay? And conversely, given an arbitrary set, consisting of elements in this domain, you could define a predicate. You could define, what you could call a membership predicate corresponding to that set. So consider a set that consists of Alice and Flamingo. I'm calling this, I'm giving the name, the set a name, club. And then I could define a predicate which is true only for Alice and Flamingo and is false for Jabberwock. So this new predicate in club, assigns true to the members of the set club and false to others. So this predicate is a membership predicate that corresponds to the set. Okay, so it should be clear that a set and a predicate are essentially the same thing. It's just two ways of talking about, the same thing, a subset of elements of your universe on which the predicate is true. Okay, so so that means whatever you want to talk about, and with respect to sets, you could translate it into the logic of predicates and propositional calculus. So let's go back to the set operations. Okay, let's start with the complement, right? So S complement Now, in terms of the membership predicate, what does it look like? So the membership predicate for S complement, which I'm writing here as in S complement, is defined as the negation of the membership predicate of S. So in S complement holds for X if and only if in S for X does not hold. Okay. So by the way, I'm writing this kind of in club or in S notation, but that's just for these examples here. We will later on always write it in the form of X's in S instead of saying in S X, right? But just for this slide, I'm going to continue using this kind of notation. Okay, so to define the complement operation on a set, I can instead define the membership predicate of that new set. And what is that membership predicate? The membership predicate of that new set is just the negation of the membership predicate of the original set S. Okay. How about union? So S union T, the membership predicate for that translates to, so X is in S union T if X is in S or X is in T. So it is simply the disjunction or the OR operation applied to in SX and in TX. Okay, so for the using the membership predicates of S and T. Similarly, intersection is the conjunction. So in S intersection T of X is simply in SX and in TX. So X is in S and X is in T. That's when X is in S intersection. So this was a unary operator, and these two are binary operators on sets. And you could also consider the the other binary operator I mentioned is a difference, which we would write as S minus T. So you would read it as S difference T or S set difference T. It's also sometimes denoted using this backslash notation. And in terms of the membership predicate, so an element is in S difference T if and only if it is in S and not in T. Now, you can always write this in terms of one of the binary operators from propositional calculus, and just happens to be the negation of the implies operator. Okay, so I could call it the not implies operator. In the language of sets, it is this negation or the complement that you would come across more naturally. Okay, so in SX, in S minus TX is true if in S X is true and in TX is false. Okay, it's the same. So you could also write the set difference in terms of the other binary operations, just like you could have done that in the case of logical operations. So S difference T is the same as S intersect T complement. Another interesting operator for sets is a symmetric difference, which simply corresponds to the XOR. So the symmetric difference of S and T consists exactly of those elements which are in exactly one of S and T, right? So X is not in the symmetric difference if it is in both of them or in neither of them. It's in the symmetric difference if it is in S or in S but not in T, or in T but not in S. Okay. These operators, the set operators, union, intersection, set difference, they're all associative operators. That's something you can immediately conclude from what you already know about logical operators. Okay. And similarly, other properties that you've seen for logical operators would immediately translate to similar properties for set operations. And here is a very useful example, De Morgan's law. So for sets, this is what it looks like. The complement of S union T is equal to the complement of S intersection the complement of T. Okay. Let's visualize this. So going back to our Venn diagram of S and T, so S union T we saw looks something like this. The dark portion again is the set, is the are the members of the set, and outside of the dark portion are not in the set. Okay, so let's bring back our looking glass, which we use to reflect propositions to their negations. Right now we do that for these sets, and the reflection corresponds to the negation or the complement in this case. So we have what it means is we just change the color. The dark portions become light and the light portions become dark. So S complement looks like this, where it's all the darkened part here, that is S complement. Okay, and similarly T complement is all the darkened part here. And what is the negation of S union T? Clearly from the picture it is this one, but what does it look like in terms of S complement and T complement? Well, the parts which are dark are exactly those which are dark in both S complement and T complement. Something which was say dark, say something here which is dark in T complement but not in S complement will not be dark here. Right? So to be darkened here, to be included in the set, it has to be included in both S complement and T complement. Okay, so that's a visualization of S complement intersection of T complement. Okay, but that's just pictures. So can you actually prove this from what we know for propositional calculus? And here is a proof. So let me translate everything here in terms of its membership predicate. So the membership predicate for S union T complement, so it evaluates to true if and only if the membership predicate for S union T evaluates to false. So this X belongs to the complement of S union T is exactly the same as the negation of X belongs to S union T. Okay, and now what do I know about the membership predicate? So this was by using the definition of complement in terms of the membership predicate. Now what do I know about the membership predicate for S union T in terms of the membership predicates for S and T? Well, we just saw, we defined this membership predicate as X is in S or X is in T. That's when X is in S union T. Okay, so the whole expression is then negation of X is in S or X is in T. And now we will apply the De Morgan's law for propositions. And we get that this is equivalent to negation of X is in S and negation of X is in T. And then we again apply the definition of the complement. So this first negation of X is in S, so X is not in S, can be written as X is in S complement. And similarly, this translates to X is in T complement. And note that this is an AND. So X is in S complement and X is in T complement. Or in other words, X is in, so now I use the definition of the intersection of the membership predicate for, in terms of membership predicates. And I get that X is an intersection of two things, by definition is X is in the intersection, X is in the first one and X is in the second one, right? All right, so X is in S union T complement is equivalent as a formula over X, S, and T, if you will, is equivalent to X is in S complement intersection T complement. Okay, so that is the membership predicate for S complement intersection T complement. These two sets are the same because their membership predicates are the same. They value to the same value on every X. And you can do the De Morgan's law for it's dual in terms of and or intersection and union, and you have the this relation here that S intersection T complement is the same as S complement union T complement. And again, okay, in terms of the pictures is what it looks like. S intersection T is this part, its complement is everything here. So things which are either in S complement or in T complement, they're all dark here. So if it's dark here or here, it's all dark here. Okay. Again, you can prove this using De Morgan's law applied to the membership predicates here. So negation of X's in S and X's in T is the same as negation of X's in S or negation of X's in T. Okay, so this duality, this kind of De Morgan's law is something you would have come across, in the case of sets, but now you see that's exactly the same thing as what we saw for in propositional calculus. Again, another property that we have seen in propositional calculus that directly translates to set operations is distributivity. So we saw that and distributes over or, and or distributes over and. In terms of, so the consequence for set operations is that intersection distributes over union. So R intersect S union T is R intersect S union R intersection T, and also union distributes over intersection. So R union S intersection T is the same as R union S intersection R union T. And again, you can reason this using the membership predicates. Okay, so those are the familiar set operations. Another statement about sets that you would often make is of set inclusion. Okay, so there's actually a relation between two sets. So for instance, here this pink set is a subset or is included in the set fly set. Okay. On the other hand, fly set and winged set are equal. Okay, so you could write these kind of relations between sets using inclusion and equality, or inclusion in the other direction. So how does that translate to in terms of propositional calculus? So S is included in T, or S is contained in T, is the same as saying that every element in S is an element in T. So in terms of membership predicate, whenever you find an element to be in S, you're guaranteed that it will be inside T, because all elements in S are inside T, right? So S is contained in T is saying that for every X, if X is in S, X is in T. If X is not in S, I don't know, it may be in T, may not be in T. But if X is in S, it is contained in T. Okay. So in this set inclusion, we could define set inclusion, in fact, as this proposition. Set inclusion is merely saying, when I say S is contained in T, it's merely asserting that for every X, if X is in S, then X is in T. And similarly, S is a superset of T, or T is a subset of S. It's again saying the same thing. It says if X is in T, then X is in S, and this holds for every X. Okay, so this you could take as the definition of set inclusion. And set equality simply is saying, X is in S if and only if X is in T. So for every X, X is in S if and only if X is in T, or in other words, S is contained in T and S is contained, and T is contained in S. That's when S equals T. Okay. In particular, the empty set is contained in every other set, or every set, including the empty set. And why is that? What does that correspond to in terms of this predicate, in terms of this proposition here? It's, this is because, so how do you ensure that the statement is true? It says for every X, if X is in the empty set, it should be in T. But for every X, if X is in empty set is vacuously true, because no X is in the empty set. So this X is in S implies X is in T is vacuously true for every X. So indeed, this statement holds for every X. So this is just, kind of elaborating on the point that the empty set is a subset of any set, and that follows from the definition of subset that we had in the previous slide. Okay. You could also similarly argue that if S is contained in T and T is contained in R, then S is contained in R. So here is a quick proof. So we can start by saying, okay, we want to prove S is contained in R. So I'll take any arbitrary element in S and show it's an element in R. There is one caveat. I cannot start by taking an arbitrary element in X if such an element doesn't exist. But in that case, we are done. If there are no elements in S, then, since the empty set is contained in R, we're already done. So suppose that's not the case. There are elements in S. Pick any arbitrary such element, and since S is contained in T, that element is also in T. And since T is a subset of R, by definition, X is in T implies X is in R. Okay, so we conclude that this arbitrary element in S is contained in is an element in R. You can also quickly verify that when I say S is contained in T, is the same as saying T complement is contained in S complement. Okay, and this is essentially just a manifestation of the contrapositive of the statement. So here X is in S implies X is in T, and the contrapositive is that X is not in T implies X is not in S, or in other words, X is in T complement implies X is in S complement. And this statement here is the same as saying T complement is a subset of S complement. Okay, so a word on when you're trying to prove that two sets are equal, often what you would do is that you would show that the two sets contain each other. So to prove S equals to T, you can show that S is contained in T and T is contained in S. And this is equivalent to proving S equals T. And as a quick example, when we're discussing numbers, we define the set L of two integers A and B as a set of all X, which can be written as an integer linear combination of A and B. And you could consider another set. You could define another set, which is all the multiples of GCD of A and B. And if you recall, we had a theorem, which we didn't state it in these words, but it said that these two sets are actually equal. It said that every element in L is actually a multiple, or they're exactly the multiples of the GCD. So they're exactly those elements that are present in M. And so that's to say every element in L is in M and vice versa. These two sets are equal. Okay. So the proof for this, as is often the case with many proofs, when you break it down into these two cases, one direction may be easier than the other direction. So in this case, the easy direction is to prove that this LAB is contained in MAB. So what does that mean? Every element in LAB is an element in MAB. So if X is in LAB, then X is in MAB. How do you prove that? Okay, so that is is the easy direction. Yeah, how do you prove that? You would just base it on the fact that if X is a integer linear combination, so if X is an LAB of A and B, and we know that the GCD divides, so let's say the GCD is G, the GCD divides A and B, then since X is an integer linear combination, it divides X also. Okay, so this is a simple consequence of divisibility. So this was the easy direction. The somewhat harder direction, which needed a little more clever argument, was to show that every element in M is actually an element in L. Okay, and in fact, the hardest part of that was to show that the GCD itself, is an element in M. We need to show that is an element in L. Okay, and that's the part which needed a little bit of argument. We showed that GCD itself is an element, and once you know that the GCD is an element of LAB, you could show that every multiple of the GCD is also an LAB. Okay, so this direction in this particular case needed more work than the other direction. And this, you might encounter often in trying to prove that two sets are equal. Going in one direction might be easier than going in the other direction. Okay, here's another thing about sets you would have probably come across. So let's take two sets, S and T, and let's try to see how big these two sets are. So they're let's just take the size. By the way, this refers to the size of set S, the number of elements in set S. So these are S and T are finite sets here. Okay, and suppose you add the number of elements in S to the number of elements in T. Well, this would so you count every element in S and every element in T, but the elements which are in both S and T get a count from here and from here, right? So they are double counted by this summation. So the elements in S intersection T are counted twice. Every other element is counted exactly once. In other words, the summation is size of every element in SU, the number of elements in S union T, plus one extra count for elements in S intersection T. Okay, so the summation is the size of S union T plus the size of S intersection T. Or in other words, the size of S union T is the size of S plus size of T minus the size of S intersection T. So this is the, this is something you would have come across as the inclusion-exclusion principle, saying that, when you want to count the size of the union, you have to, you can take the sum of the two set sizes, but you have to then discount the number of elements in the intersection because they got counted twice. So you have to discount them once. You can go from go to more sets, more than two sets. So here is what it will look like for three sets. So the size of R union S union T is, first you can just sum up the size of 3 sets R, S, and T, then you realize that, okay, things in R intersection S were counted once by R and once by S. So you subtract them. So you subtract R intersection S. Similarly, you subtract R intersection T, and you subtract T intersect R. But now you have a little bit of trouble because the elements in the intersection of RS and T, they were subtracted thrice, right? They were subtracted in each of these cases, and they were counted also thrice. So they were counted thrice and discounted thrice, so we are not accounted for them yet, so we add them back. Okay? So this is what the inclusion-exclusion principle looks like for three sets. Now this thing actually can quickly prove from this statement for 2 sets, and here is what a proof would look like. So you just think of S union T as a single set initially, and you use the inclusion-exclusion principle to say, okay, what is R union S union T? What's the size of that? That's size of R plus size of S union T minus the size of the intersection between R and S union T. And then you expand this using the distributive property, and then you expand S union T using the inclusion-exclusion principle for 2 elements, and this is what you are left with. Okay, and again, this R intersect S union R intersect T, again you need to, so you expanded it using the distributive property. Again, you apply the inclusion-exclusion principle to that. So that's where you get this 3 terms here, R intersect S plus R intersect T size minus the size of the intersection of R intersection S and R intersection T, but that's the same as size of R intersection. That's the same set as R intersection S intersection T. It doesn't matter that you intersect it again with R once more. Okay. All right. So this is a useful property to remember, and it would be useful when you're doing counting arguments later. I'll finish with one last thing that you probably are already familiar with about sets, and that is the Cartesian product. Okay, so the product or Cartesian product of 2 sets is defined as simply the pairs of elements where the first element in the pair comes from the first set and the second one comes from the second set. Okay, so S intersect T consists of pairs of elements of the form S comma T, where S is in the set capital S and T is in the set capital T. So if I were to visualize this, I just drawn this little Venn diagram of the set S. So this yellow thing is its universe and the red part is the set S. I've drawn it in this kind of a one-dimensional way so that I can visualize S cross T. So T is another set, potentially another universe, or it could be the same universe. So I've drawn it separately is another universe with the set T highlighted there. And their cross product is a different universe. It's neither the universe of S nor the universe of T, so that this green box here. And the S intersection T, you could think of each element here as corresponding to an element in S and an element in T. Okay, so if, for instance, if this were these S and T were intervals of the real numbers, and these were the x-axis and the y-axis, and there's a square or there's a rectangle in the real plane that will correspond to the Cartesian product. Every element in that Cartesian product corresponds to a pair of elements, the first one from S and the second one from T. Okay, so that's like the x pairs, the coordinate pairs x comma y in the xy plane when you do geometry. right? Cartesian geometry. Okay. A special case of interest is, when does a set become empty? When does a cross product become empty? But there's also called the cross product. It's empty if and only if at least one of S and T is empty. So clearly, if one of S and T is empty, there is nothing here, right? Because the set consists of elements where first one has to come from S and the second one has to come from T. So if S is empty, there are no such elements. Similarly, if T is empty, there are no such elements. Conversely, if S and T were not empty, so then there is at least one element in S and one element in T, then that pair of those two elements would be in S cross T, and S cross T will not be empty. So S cross T is empty if and only if at least one of S and T is empty, maybe both. More generally, the size of S and T is exactly the size of S times the size of T, right? Again, that follows from the fact that in fact, this could be used as a definition of multiplication if you want, but for us, this is just an obvious fact. Now, you could also do Cartesian product for more than two sets. So R cross S cross T consists of triples of the form RST, where the first element comes from R, second from S, and the third from T. It's not quite the same as R cross S cross T, because R cross S cross T, so R cross S already consists of pairs of elements of the form RS, and R cross S cross T consists of elements of the form, pairs where the first element is a pair RS and the second element is an element T from the set T. Okay, so this pair, in which one of the elements is a pair, is not quite the same as this triple. However, they're essentially the same. There's a one-to-one mapping, that'll let you translate from these kind of pairs to these kind of triples. Okay, so they're essentially the same, but syntactically they're two different objects. You can, how does cross product distribute over union and intersection? Well, it distributes. So A union B cross C is A cross C union B cross C. So to visualize this, suppose here is our A and C, and this is our A cross C. And suppose I consider another set B, right here, the thing in pink, which overlaps with A little bit. And now B cross C is the box that appeared here in the bottom. And A union B cross C is this entire bigger box here. And that can be written as a union of two smaller boxes, one that was already there as A cross C, and the other B cross C. Okay. Also, the intersection, if you look at A intersect B, which is this region here, and its cross product with C is just the middle box that you see here. If you carefully look, the box in the middle is in a slightly different color, and that could be written as the intersection of the original box A cross C and the new box B cross C. Okay, you can also quickly see this by from the definitions themselves. You can also consider here I had a single C. What if we have C union D or C and D there? Then say I just added another set there D, and A union B cross C union D. Now you have these extra boxes here, and the whole A here, and that could be seen as a union of four things, namely A cross C, B cross C, A cross D and B cross D. Okay, so that is the union of that's a cross product of A union B cross C union D, and similarly the intersection, A cross A intersection B cross C intersection D, that is in the intersection of those four boxes. And finally, what is the complement of the cross product of two elements, two sets, S cross T? So to visualize it a little better, I've drawn S and T to one end of my picture here. So S is the darkened part and S complement is a lighter part. And similarly here T and T complement, and part is S cross T. So its complement is everything outside here, which you could write as the union of three sets, namely S complement cross T complement, which is here, S complement cross T, and S cross T complement, right? So just pay attention that S cross T complement is not just S complement cross T complement. There are these other parts also to it. All right, so that's it for now, and we'll continue with relations in the next video.